Okay, so let's pick back up with this. When we left off with logical agents, specifically knowledge-based agents, we looked at Wampus World, and we saw how going through the environment and using the rules for the environment, 20% chance there's a pit, when you feel a breeze, that sort of thing, that helped us make decisions. We use that information to make it through the game itself and win. We know we had to make some choices that were kind of risky, but the purpose of this is to make the best choice from what we have available. And so what we want to look at now, and we're not going to spend a ton of time on this, but I just want to explore how we would actually implement something like this. So if we have a situation where we have an environment with clearly defined rules, how would we code an agent to play through the game in the same way that we did as a class just a little bit ago? Okay? And it gets kind of tough because we're balancing a lot of different information all at the same time. There's a breeze in this tile, there's not a breeze in this tile, there's a stench here, there's not a stench there, combining those to make logical choices. So the first thing that we need to do is look at how we're going to represent those truths. And so when we look at representing logic as sentences, we've already talked about these sentences are the truth, the axioms that we know about the environment. The idea here is that it is simple with no gray area. It's either true, it's either false. Okay? We look at some examples here of how we would do that. Okay? Those are kind of generic implementations. Let's move down and apply this specifically to Wampus World. So entailment is when we talked before about the inference mechanism. Entailment is when one sentence follows logically from another sentence. When we were playing the game just a little bit ago, did we use this? Did we use entailment? Was there or was there a situation when this occurred?
Yeah.
Yes. When? One example.
When you were making that decision at the end to go forward instead of back.
Okay, good. All right. So if we look at this is a representation of the environment. And at each of the positions, we see the different notations for what's there. When we start, we're right here, and we haven't discovered anything yet. A means the agent's here. OK means that we know that that particular tile, square, node, same thing. We know that it is safe. Okay? So because we perceive no breeze or stench, we know that the adjacent tiles are safe. The only time we can determine that one is not safe is if we perceive a breeze or a stench. Okay? So we perceive nothing, so we know both of these are okay. Now, do you guys remember, which way do we face when we start?
Right.
We face right. Okay? And so the easiest thing for us to do is just to move forward. Okay? Because that costs us 1 point. But if we were to first turn and then move forward, this would cost us a total of 2 points, which is why it's more logical just to move straight forward. Okay? We want to avoid unnecessary movements.
So turning counts.
Turning is an action, yes. That is correct. Okay? So we make the move and we end up here. So the agent is now here. V means we have visited this. So if we were talking about this in terms of A star terminology, this would be in the closed list. Okay? We're here and we perceive a breeze. Now we perceive a breeze, and that tells us that there's either a pit here, and so we have pit question mark, or a pit here, pit question mark. And this leads us to the idea of a model. And a model is a term that refers to a possible world or environment. And so there's two models that we can go to from here. There's the model where this is a pit. I guess there's three. There's a model where this is a pit, and there's a model where both of those are pits. And those are the only three models that could come from the information that we have. Okay, let's move it on. So we're going to flip back and forth between these two. Okay. So, based off of what we have discovered so far, we can come up with 1, 2, 3, 4, 5, 6, 7, 8 different possible world combinations. Okay? Again, look. We have so far looked at these right here. Okay? Now we have visited this one and we visited this one. So we know what's there. So what we're doing now is we are creating different models, which we've said models are possible worlds. They could exist. So we are going to create all of the different possible models that we could come up with. And that's what we get with this down here. Now, why are some of these in red and why are some of them in blue?
The red is the knowledge base.
Good. So what we have done here is, based off of what we discovered above, and let me write this here. We'll write this off to the side, okay? Do a smaller version. Okay, is it V? Okay. There's a breeze here, but it is okay. Pit, question mark, pit, question mark, okay. That's what we know so far. So when we come down here and we look at the models that we generate, why is this one in blue? Is this possible?
No.
No.
Before we knew that this was a breeze, was this possible? Yes. Yes. Well,
No, because the pit.
you're right, let me say this. Before we got into the world, was this possible? Okay? Was this possible? Were any of these possible before we got information about the world?
Yeah.
Okay? So here's what happens. Remember we said this last time. When we come into this, the obstacle that we have to overcome is our initial ignorance. Any of these worlds could exist. Lots of them. Any of these worlds could exist. So what we have done is, when we moved here and we said, there's a breeze, we said, can't be this, can't be this, can't be this, can't be this, can't be this. As we go through and we discover new information, we eliminate these. Okay? Now, we didn't eliminate all of these when we moved here. Some of them we eliminated when we first moved into the world. Which ones did we eliminate when we first moved into the world? When we were at tile 1-1, we were able to eliminate some of these. Which ones were that?
2 times.
Yep. When we were here and there was no breeze, we said, can't be this, can't be 2.
Can't be. It can be.
Yes,
It can be
that.
It could be. Because we didn't know about.
Could be this one,
Can't be
can't
that.
be this one,
Can't be that.
can't be this one,
Cannot be that.
can't be this one. So once we moved and there was a breeze here, then we get rid of this one. So do we agree that the 3 that are remaining are all possible? Yep. Okay. So what happens? So the agent is currently here. I'm sorry, the agent is here, moves back here, turns, moves up here. If there is no breeze here, if he detects nothing, which of these can we eliminate? Yep. Now, this is just one way to do it. Creating a bunch of different models and eliminating the models based off of the information that we receive. So here's what I want you guys to do. I want you to take about 3 minutes. And I want you to come up with at least the beginning parts for how you would represent this in code. Okay? We just talked about an example. Agent comes into the world, they perceive nothing in the first tile. They move forward and they perceive a breeze. Could be a pit in either of these two places. They turn back and come up here. Everything that the agent did, that we described that we would do, is logical. It is the correct move. But the key here, and what I want you guys to take a few minutes to try to figure out is, how do we represent that knowledge in code so that what is produced from the agent is consistent with what we would do? Okay? So take a few minutes, and then we'll talk about what you come up with.
I have a question.
Yo.
Would the agents have knowledge of the size of the world to begin with, or no?
In this example, yes, but in an environment that is perhaps larger than 4.4 and they don't know, they have built in, if you go up, if you are here and you try to move forward, it would say bump.
Okay.
In which case you could determine the bounds of the world.
Gotcha.
Yes? Question? No questions? All right, so take another minute, kind of plan this out.
Well, I guess instead of having like left is just the object, or like the references left, right, whatever else you got, like this object, it has an array with like the first index being an object is either null or the object itself, and the next index is either C3 or what's it called, or nothing, like basically, so we just hit glitter from so none of those are that's why the tag is having a good array of two layers, so you have two items at the same time. We're going to another year, so first index is the index, right there as well. Next index is whether or not those that's also get midway through go back to the
All right, let's talk about this. Who's got an idea? How would you represent this in code? Okay, let's go.
So I thought, so if the agent spawns in a room, it looks at what it currently knows about the environment. Like in this example, if it spawns in that corner, it knows that there are at least 3 rooms in the environment. And those 3 rooms can have 3 possible different configurations. So it would make a list of possible states where there are 3 rooms with 3 different configurations. So that would be 27 different states that could exist. And then it would eliminate the ones that it knows exist, and then choose the safest route, and then update the list based on what it mapped as well.
Very good. Very good. That's a good approach to it. Got another idea?
Yeah, couldn't you like have set values for certain characteristics so you know like the rules of the world itself? So you know like there is a wampus, there is a pit, you know a room can be safe, you know if you run into a wall you don't do anything. And have certain values set to those and run logic on a combination of those values through some complicated algorithms, which could get very confusing quickly. But it would seem less intensive than running through an exponential amount of states.
Yep, definitely another way to do it. Good. Yep.
So I did, while the game is running, move forward, get room status, calculate options, calculate shoot probability, take possible action, change directions.
Did you talk about how you calculate your options? That's a good outline, because I think...
It's in another method called calculate possible options.
So let's look at this. Let's take a look at an approach like this. So, and again, as you guys are kind of going through this, and we just heard from a few different people about some approaches, there are multiple ways to solve this. Just like there are multiple ways to do your 8 queens program. We just happened to select the hill climbing algorithm. There's other algorithms that we could use. Just like there are different approaches to this. Could we use A star for this?
No, because you don't know your whole base star doesn't know.
No,
No, because it's
because
not,
we don't have an end node.
and it's partially visible.
You have an end node. You do have an end node, but you don't know which index it is.
So, yes and no is the answer. We would use a modified A star. A star. Now, you're right, we don't have a goal node. What we do, we just don't know what it is yet. And the goal, really, is to continue to explore until we find the gold. When we find the gold, we found our goal node. Okay? So let's just play around with this idea a little bit and explore how we would use A star. So we know A star is predicated off of the F equals G plus H, where we move based off of continuing to select the node that has the best F score. Whether best means higher or lower depends on the situation. So in this situation, we've got two values. We've got a G and we've got an H. Do we care about G? What is G?
This is between current node and the end node.
Okay, yes, it's the cost. Cost in these kind of environments are typically referred to as distance. In this situation, because our performance measure is defined in terms of actions, then we would say G is the number of actions so when we're trying to decide which node to move to, when we're considering the G, we are going to look at the cost to get to that node from our node. H. What's the heuristic of a node in this situation? We know that heuristic is an estimation of how good it is.
Can you assign values to like gigs and
Sure can.
based on that?
Now again, we can't use A star like we used it before because we don't know where stuff is. And each time we make an action, we reevaluate. Whereas A star is not like that. A star plans out the whole process because even though it can see incrementally, it knows where the goal is before it starts. Okay, so we can't use A star like we did before. But we can still use this as the decision making for where we go. Right? So when we first start and land here, we generate our neighbor nodes here and here. So these are our possible moves. The G cost of this would be 1. The G cost of this would be 2. The number of actions necessary to get to it from the current one. Because you have to turn and then move forward. Okay? Now, the heuristic, when we did our first A star program, was an estimated distance from that node to the goal. In this situation, our heuristic would be the likelihood that we're going to die if we move there. Are we going to die if we move here? No. So our heuristic would be 0. Heuristic would be 0. So we take these two, add them to the open list. Where are we going to move? This one. Excuse me. We're here, and now we generate 2 more nodes. Excuse me. Now, we'll have to play with the G cost a little bit because each time we move, the G cost changes. Okay. So that's fine. What we would do is we would keep track of how far we moved from the node that was used to generate that one and add that onto the G cost. So now the cost to move here would be 3 because you have to turn move. You actually turn twice, but
Isn't it 4?
it would be, because you have to turn twice and then back, or 3 times actually. Either way, when we look at this, this is still on our open list. Okay? We also have the addition of these two. So what might make more sense, instead of using the G cost as the number of actions to get there, it might make more sense just to store where those tiles are, and when we look at them, only take G into consideration if the H values are the same. So if we've got 3 moves that all have the same heuristic, we're going to select the one that is closest to us. Okay? Does that make sense? Because this is, again, a little bit different than H star, so we'll have to modify it that way. Now, here's the key. We said the heuristic of this node was 0. What would the heuristic of these be?
1,000.
1,000?
500.
500?
There's a cookie either one.
Not 0.
Not 0. Good. There's a chance that we could die when we move here. Okay? Here's what I'm getting at. Okay, if we have a situation where there's a breeze, we know that this breeze could come from any of these 4 adjacent places. But if there's not a breeze here, or let's say there is a breeze here, but there's not a breeze here, we need some way to scale the heuristic based off of the number of adjacent breezes. Does that make sense? So in this situation, we've got a breeze and a breeze. How likely is this pit?
100%.
Is it?
No, because it could be.
No. We could have a pit here and a pit here, and that's it.
Just add
1 out of 5.
Just add 1 based on the number of adjacent breezes. So it's a little bit more risky the higher that value is.
The more breezes adjacent to it. But is there a way that we can calculate it more definitively?
Yeah, like if there was no breeze in 3-1, you would know that 3-2 doesn't have a pit.
Okay. What if we haven't gotten here yet?
Question.
Okay. So this is where it gets tricky. When you have a breeze here, you look at the number of adjacent tiles to the breeze. Okay? In this case, there are 3. There's 1, 2, 3. So there are 3 contributing factors to that breeze. So it's different from where if we have a breeze here. This breeze tells us a lot more than this breeze does. Okay? Because we know that this breeze is coming from either here or here, where this breeze could come from any of the 4 adjacent ones. So we need a way to update this. So we need a way to show that scale. Okay? So if this breeze, let's say we look at this one right here. We can scale it based off of 2 things. The first is the number of adjacent tiles to the breeze, in addition to the number of tiles that are outside of the bounds. If we are kind of creating ones, if we're looking at this, and we create this one up here and here, these would not be considered and would subtract from it, because this breeze is more likely to come from here or here. So we scale the heuristic. Maybe, as someone suggested just a little bit ago, we add 1 for each additional breeze. So if we're trying to figure out if this is a pit, if there's a breeze here and there's a breeze here, then we add 1 for each adjacent breeze that we found. And we also add 1 for each of those breezes that have sides that don't belong in the bounds of the world. Okay, so for example, this breeze would actually contribute +2 because it hits here, and 1 because there's one tile outside of the bounds. This breeze would only contribute +1. Okay? Whereas if we had a pit here, this breeze would contribute +3. This one would contribute +2. This one would contribute +1. Does that make sense? Is this for certain?
Do you know, like, where, you don't know where these breezes are yet, because you haven't explored it.
Correct. And when we hit, let's say we're right here, even though this might be pit, we don't know, per se, that this breeze backs up to a wall. So that's why we have to continue to update as we go through. You guys see, it was a movie. What was it? It was about counting cards. Blackjack. 21.
21.
There was an example given in that movie about variable change.
Wasn't it that door thing?
Yeah, that's exactly what it was. So,
Reveals the door, it's 2/3 better to change or something.
if you, here's it explained. Let's see if I can get it right. You guys, any of you remember Let's Make a Deal? Like the original one before, who does it now?
I wasn't alive, but I know what it is.
I remember watching Let's Make a Deal, showing my age. Let's Make a Deal. In that show, they would do a lot of crazy things. But one of the things they would do is they would say, all right, let's say there are 3 doors. Okay? Behind 2 of the doors, there's basically nothing. Behind the 3rd door, there's $1 million. Okay? And you get to pick. Okay, and let's say you pick, okay, I'm going to pick door number 2. Okay? So you make your choice. And then the guy who's running the show says, you know what? You can stick with door number 2 if you want. But I'm gonna go ahead and take away door number 1. Door number 1 didn't have anything behind it. And I'm going to let you choose whether you keep door number 2 that you picked initially, or you can change and pick door number 3. Should you do it?
Yes.
The answer is yes. The but always comes, but it's still 50-50. But it doesn't matter. There's still a 25% chance, whatever you want to say, depending on how many adjacent breezes there are. But it's not. It matters when you picked. You see, initially, when you picked, you were deciding between how many doors? 3 doors. What is the probability at the time that you picked, and that's the key, at the time that you picked, what is the probability that you picked the right door? 1 out of 3, 33%. Good. Now, once the host removes one of those doors, if you stick with your pick, what is the probability that you picked the right door?
1/3.
1/3.
Switching is 2.
If you switch, what is the probability that you picked the right door? 50%.
No, but the thing is, so there were
Okay? Now, if that's confusing to you, let's take it, let's blow it up a little bit bigger. Let's say instead of there being 3 doors, there's 1,000,000 doors. Okay? Or what's the case where you've got what's the game where you've got the cases and they open it up, there's like money inside of it? Same thing. That game does the same thing. How many cases are there when you start?
24.
A significant.
30. No, 30.
30 cases. Let's just say there's 30 cases. Let's say there's 30 cases. And when the game starts, if for those of you that don't know, you start the game and there's like 30 briefcases. And there's like people standing next to the briefcases. And there are dollar amounts inside of the briefcases. Okay, anywhere from like $1 to...
1 cent to 1,000.
Okay, so we'll just say it's anywhere between 1 cent and $1 million. With increments in between. So there's probably like a $100 one, a $500 one, a $10,000 one, that sort of thing. Okay? So at the beginning of the game, you pick a briefcase. You could get the 1 cent one, you could get the 1 million one, you could get the $5 one. Who knows? Somewhere in between 1 cent and $1 million. So as the game goes through, you eliminate briefcases, and they open them up, and they make you offers based off of what they think might be in your briefcase, based off of the probability of what is remaining. So you make it through, keep going. It eventually gets down to the end when there's only 2 briefcases. And it just so happens that the only $2 amounts left are 1 cent and $1 million. I'm sure, has that ever happened? Anybody?
Yes.
It has happened?
It happened like 3 or 4 times, yeah.
Okay. So you have 2 briefcases. The one you picked at the beginning, you have no idea what's in it. And the one that's left, that's still up there, you have no idea what's in it. You know one of them has 1 cent and one of them has $1 million, but you don't know which is which. And I don't know if they do that in that show, but do they give you the option to switch?
Yeah.
Very end.
Should you switch at the end? The answer is yes, every time. And the reason for that is, think about the probability. And now, it matters so much when you made the decision. See, when you picked that case initially, you picked between 1 of 30 cases. What is the probability, roughly, that you picked the $1 million case out of 30? 3% chance-ish. Not very good. At the very end, when they give you the option to change, if you pick the other case, what is the probability that you pick the correct $1 million one?
29 out of 30.
Is it 29 out of 30?
I think.
Or is it 50-50?
29 out of 30. So you've seen all the others. You know that they don't have anything. Yeah, no, it's 1 out of 30 for the first case, but then 29 out of 30 for the last one. So you know the others don't have the 1 million in it.
No, because they're removed from the equation. They aren't still there.
The
It ends
variable
up being
change.
50.
But with that Monte Carlo one, let's make it still 2/3 when you want to switch.
Because you're not picking from
Even
all the
though you
open
removed
cases. It's now, there's this case and that case. You don't.
It's the same
The
thing.
chances
It's
of one and
2/3,
two.
right?
If he's right now, then I'm in class.
But with that
So what is it? Is it 29 out of 30 or is it 50-50?
Because there's only 2 left.
How many are you deciding between?
2.
true.
Just 2. How many of you are confused by this? So here's the key. When you make the choice matters. If you had 1 million cases to pick from, the probability that you pick the correct case is 1 of 1 million. Question? So you're saying I got a joke? I'm glad one person got that joke. Okay, showing my age. There's 1 out of 1 million. Now, if we go through and we eliminate 999,998 of those, and you're down to 2. You know one of them is the correct, and one of them, just like all of the other ones, don't have anything in them. When you make the choice at that time, if you choose the case that you picked in the beginning, it's not a 50% chance. And this is where it confuses people. But you're like, but you're picking between 2 cases. Yes, but when you pick that case, the reason you have that case is because you selected it from an initial population of 1 million cases. So the chances that the case that you have is correct is 1 out of 1 million. But if you switch and you pick the other one, because you have eliminated 999,999 incorrect ones, if you switch, there's a 1 out of 2 or a 50% chance that you'll pick the right one.
Don't they have to add up to 1 though? It probably always adds up to 1.
If you look at it from, you're right. If you look at it from that perspective, what is the probability that picking the first one is going to get you $1 million? What is the probability of picking the second one? They're both 50%. But what you aren't taking into consideration is how you got that first one there. And so when you, and again, this is why this is tricky, why so many people screw up on game shows. It's when you started that matters. So when you pick that first case, you picked from 1 million. If you don't change when you're given that opportunity at the end, then the probability that that is correct is still the initial probability because you haven't changed your selection. But if you change, then you're picking between 2 cases. Yes?
Well, why is it for that let's make a deal problem, why is it that it's 2/3 chance when you switch instead of 50-50? I mean, I know the first one you picked is a 1/3, like, has a 1/3 chance of being right, but
It's
afterwards it should be like 2/3, because like there are 3 different scenarios. You either pick the right one, or you pick the wrong one, or you pick the wrong one.
So that's if you, and again, the different numbers that we're coming up with all come into play depending on when you look at the situation. So when we say it's a 50-50 chance, that's when we're looking at the very end. If we look at it at the beginning and we say, what is the probability that you pick it correctly from that situation, if you know you're going to change at the end, again, because the probability has to add up to 1, that's where you get the 2/3. That's where you get the 999,999 out of 1 million chance if you know you're going to switch at the end.
Yeah.
So what you're saying is correct. It is 2/3, but it's looking at it from the perspective at the beginning, not at the very end when you make the choice. But if that makes sense.
Yeah.
So yes, it is 2/3, but when we're talking about it being 50%, that's when we're making a choice at the end. Right. Other thoughts, questions? Okay, so again, how that relates to this, you have to look at the heuristics that we're calculating at the time when we're trying to figure out, is it safer to move here or here? We know that there's a chance that we die if we move into any of them. We have to look at when we made those decisions. And if any of the probabilities have changed, if we have eliminated or gathered new information, because that would affect the likelihood that that tile is safe. All right? All right. So we went through this before, and we've kind of talked about this already. We're not going to get into this much, but the idea of writing axioms, truth statements, combining them in inference mechanism, having entailment and that sort of thing, that's a huge part of AI. So sometimes it's known as prepositional logic, sometimes it's called first order logic. There's lots of different places to go from here. Okay, but this is kind of the beginning part when we're talking about making choices about an environment in a logical setting. Robotics and stuff like that goes down this path. Okay. We talked at the beginning of the semester about the fact that this is kind of an introductory AI. It gets you exposed to all the different areas. But what we are doing here has a whole very long, deep path. There's some grad courses, intelligent systems, that takes this and goes farther with it. Okay, if that is something that interests you, just know that that's out there. We obviously aren't going to cover it here. It's beyond the scope of what we're going to do. Okay? So that kind of wraps us up with what we're doing with the knowledge-based agents, logical agents with multi-score. Okay? Are there any questions? Okay.